a man with wild hair, an iconic mustache, and a sparkle of genius in his eyes. That's Albert Einstein, the man who dared to challenge conventional scientific thought. His experiments were not just about test tubes and beakers. They were thought experiments, pushing the boundaries of imagination and intellect. Einstein's work, a brilliant blend of creativity and logic, reshaped our understanding of the universe. His unconventional approach to scientific exploration was a breath of fresh air in an era of strictly empirical methodology. His theories, once considered radical, now form the bedrock of modern physics, impacting everything from space exploration to GPS technology. Einstein's genius lies not just in his theories, but also in the unique way he conducted his experiments. His legacy continues to inspire scientists and thinkers worldwide. Join us on this journey as we delve into the fascinating world of Einstein's experiments. Our journey begins in 1905 with the birth of Einstein's special theory of relativity. A young Albert Einstein, working in a patent office in Switzerland, questioning the very fabric of the universe. He's not in a lab, there are no test tubes, no microscopes, just a man with a brilliant mind grappling with the mysteries of space and time. Einstein's special theory of relativity, published in his miracle year, was nothing short of a revolution in physics. At its heart lay a deceptively simple equation. E equals mc squared, or as we all know it, energy equals mass, times the speed of light squared. But what did this really mean? The equation tells us that energy and mass are interchangeable. They're different forms of the same thing. This was a radical idea, a complete departure from the classical physics of Newton. It implied that a tiny amount of mass could be converted into a huge amount of energy and vice versa. This was more than just a scientific curiosity, it had profound implications. The equation E equals mc squared was the key that unlocked the atomic age. It explained how the sun and other stars shine, converting mass into energy through nuclear fusion. It paved the way for nuclear power and unfortunately for nuclear weapons as well. But the special theory of relativity wasn't just about energy and mass. It also introduced the idea that the laws of physics should look the same to everyone, no matter how fast they're moving. This was a fundamental shift in our understanding of the universe. It told us that space and time are intertwined in a four-dimensional space-time fabric, and that time itself could slow down at high speeds. Einstein's special theory of relativity was a game-changer. It challenged our preconceived notions, it made us question our understanding of the universe, and it opened up a whole new world of possibilities. This groundbreaking experiment set the stage for the future of physics. Fast forward to 1915, where Einstein introduces us to the general theory of relativity. This wasn't just a sequel to his special theory. It was a whole new blockbuster, fundamentally altering our perception of the universe. The general theory of relativity is all about gravity. But forget about apples falling from trees. Einstein had a whole new take on it. He envisioned a universe where space and time are interwoven into a single entity, space-time. Imagine a rubber sheet that can be stretched and deformed. That's space-time. And massive objects? They don't just exist in space-time, they shape it. This is how Einstein interpreted gravity. Not as a force, but as a curvature of space-time caused by mass and energy. Now, what's a groundbreaking theory without a bold prediction? Einstein's general theory of relativity predicted that light would be bent when it passes close to a massive object. This was a striking departure from Newtonian physics, which viewed light as immune to gravity's pull. So how do you prove something as mind-bending as this? You wait for a solar eclipse, of course. And that's exactly what Sir Arthur Eddington did in 1919. By observing stars near the sun during a total solar eclipse, Eddington confirmed that their light was indeed bent as it passed the sun. The amount of bending? Exactly as Einstein's theory had predicted. This experiment was a game-changer. It confirmed that Einstein was right. Light doesn't always travel in a straight line. When passing close to a massive object, it follows the curve of space-time. This was a revolutionary idea, and it validated the general theory of relativity. And so, with this theory, Einstein didn't just give us a new way to look at gravity. He gave us a new way to look at the universe itself. He showed us that the fabric of the cosmos is not a passive stage on which the drama of physics plays out. Rather, It's an active participant, shaped and reshaped by the mass and energy within it. Once again, Einstein had reshaped our understanding of the universe. In the 1920s, Einstein delved into the world of quantum mechanics, giving rise to the quantum revolution. As the world was still reeling from the revelations of relativity, Einstein, ever the relentless explorer of the universe, turned his gaze towards the microscopic world. His journey into the quantum domain began with a simple question: why does certain light eject electrons from metals? It was a phenomenon known as the photoelectric effect, and it puzzled scientists of the time. Einstein proposed a daring hypothesis. He suggested that light, which was widely regarded as a wave, could also be thought of as a stream of particles. These particles, which he called quanta, or photons, were like tiny billiard balls of light. Each photon carried a specific amount of energy, enough to knock an electron out of its orbit in a metal atom. This was a radical departure from the traditional understanding of light. It was an audacious proposition, one that introduced the concept of wave-particle duality. Light was not just a wave, nor just a particle. It was both, simultaneously. This was a concept so profound, so contrary to our everyday experience, that it shook the very foundations of physics. Einstein's work on the photoelectric effect won him the Nobel Prize in Physics in 1921. But more than that, it laid the groundwork for the development of quantum mechanics. His ideas sparked a revolution, a quantum revolution that led to the development of technologies that power our world today, from lasers to MRI machines and even the computer you're using right now. Einstein's journey into the quantum world was not without controversy. His ideas were met with skepticism, and even he himself had doubts about the strange and counterintuitive world of quantum mechanics. But his relentless pursuit of understanding, his audacity to question and challenge the status quo, led to a profound shift in our understanding of the universe. Einstein's quantum revolution deeply transformed our perception of reality. His legacy continues to inspire and challenge us, reminding us that the universe is far more fascinating and mysterious than we could ever imagine. Einstein's experiments have left an indelible mark on the world of science. We've journeyed through the enigma of Einstein's experiments, from the dawn of his theory of relativity to the quantum revolution. These weren't just experiments. They were milestones that redefined our understanding of the universe. Einstein's work on the theory of relativity, both special and general, revolutionized our perception of space and time. His famous equation, E=mc2, showcased the profound relationship between mass and energy, reshaping the field of physics. His general theory of relativity, with its mind-bending concepts of warped space-time, opened the door for the study of black holes and gravitational waves. It has been a cornerstone for cosmology, the study of the universe's origins and evolution. The quantum revolution, where Einstein questioned the very foundation of quantum mechanics with his "God does not play dice" argument, still echoes in the hallways of modern science. His work on the photoelectric effect, for which he won the Nobel Prize, is fundamental to today's quantum technologies. But the legacy of Einstein's experiments extends beyond his own work. His relentless pursuit of knowledge, his audacity to challenge established norms, and his unfettered curiosity have set a precedent for the scientific community. Einstein's experiments have become a beacon, guiding scientists across generations. They continue to inspire new theories, incite debates, and fuel research in various fields, from particle physics to cosmology, from quantum computing to gravitational wave astronomy. The impact of Einstein's experiments is not confined to the realm of science. They have permeated into our everyday life. GPS navigation, nuclear power, and even the screen you're staring at right now owe their existence in some way to Einstein's groundbreaking work.